Hi, my name is Jonathan Doolin, and I'd like to introduce you to the idea of temporal facing. What I mean by facing here is the idea that you have a forward and back, an up and a down, and a left. Well, that would be his right, wouldn't it? Okay, left and right. These are directions of instantaneous facing. You are now facing forward. In the next moment, you could turn to your left, and all of the objects around you would change their coordinates. So the things that were to your left become forward. The things that were forward become to the right. And the things that were to your right are now behind you, etc. These directions are observer dependent. That is, your forward direction and my forward direction are probably not the same. That is, unless we are both standing or sitting together facing in the same direction. If Bob and Barbara are facing opposite direction, then Bob's forward direction is that way, and Barbara's forward direction is that way. So, forward, back, left, right. We're all pretty familiar with these concepts and how you can turn to change what was your left and make it your forward, or put it behind you. The operation is known in technical circles as a rotation. And when you rotate so that your perspective changes, the things that were once in front of you are now behind you. Now, this is the philosophical detail that people will get hung up on. When you rotate your own body, people will say that the coordinates of the objects didn't really change. However, if you have defined your coordinate system based on the directions forward, back, left, and right for the turning observer, then the numbers did indeed change. The operation involved is called a rotation transformation. And what the rotation transformation basically does is it moves objects around the observer in circular paths. As the observer rotates from a direction forward to a direction, let's call it forward prime, through a given angle, let's call it theta, nearby objects move just a small distance, while faraway objects move a larger distance. Now, of course, some might say this is absurd. These objects are not moving at all. All that is happening is that the observer is changing its facing. However, if we use the math that defines coordinates, say x, y, and z out of the page that are based on the observer's right, forward, up, we have to embrace the absurdity that the coordinates of objects in that coordinate system, based on the observer's facing, the coordinates of those objects is in fact moving. It's changing, and you might as well call it moving. Mathematically speaking, the rotation transformation looks something like this. If you rotate counterclockwise by an angle theta in the xy plane, then your new x, called x prime, corresponding to this direction forward prime, will be the cosine of the angle theta times x minus the sine of the angle theta times y. And your new y, called y prime, will be the sine of the angle that you've turned times x plus the cosine of the angle theta times the old y. Actually, that's the transformation for the observer turning clockwise, so that things would appear to move counterclockwise to the observer. If we want the observer to turn counterclockwise and the objects to turn clockwise in his view, then the signs on the signs have to be reversed. Okay, so that covers normal instantaneous facing. This is a concept that most people are familiar with if they've ever had to walk around or turn their head. The idea I'd like to introduce now, though, is called temporal facing, and this is the idea that, like the forward direction in space, we have a future direction forward in time, which we can control at will. How can I control my future direction? Well, right now I'm sitting in a chair, hunched over a desk, facing a nice big flat screen monitor. I also have a lamp sitting next to my desk. Now, as long as I don't change my temporal facing, then that events that lie in my future include being hit by photons that emanating from this lamp and this computer monitor. But if I did change my temporal facing, then there could be any number of events that lie in my future, such as going to the living room, or going out for a jog or a bike ride, or going to the coffee shop. Now, there's a fairly familiar idea in physics called a spacetime diagram, or a Minkowski diagram. The spacetime diagram is at its heart a very simple idea. You draw two coordinate axes. Wait, let's use black. One representing time, usually vertical, and the other one representing space, usually horizontal. Then, if an object is not moving, such as me in my chair next to a flat screen computer monitor, then that path is represented by a vertical line in the spacetime. Here I am at position x equals 1 as time moves forward into the future. If in 1 hour I decided to stand up and move forward, I would eventually get to x equals 2 into the living room, x equals 3 out the front door, x equals 4, 5, 6, all the way to the coffee shop, where I would stop. And my so-called world line would go vertical again. Now, this is a simple idea of a space-time diagram and a world line of an object moving through it, or more specifically, an observer moving through it. But let's discuss my temporal facing during this journey. In the beginning, my temporal facing was the same direction as the chairs. And at the end, my temporal facing was the same as the coffee shop. But in between here, while I was moving at a constant rate from my chair to the coffee shop, my temporal facing lay in an entirely different direction. What happened was that I accelerated. I accelerated to change my temporal facing so that this event at the coffee shop would lie in my future. And then, when I got to the coffee shop, I decelerated so that I shared the temporal facing with the coffee shop. Now, this is where I'm going to break with more traditional convention. I'm going to imagine a new spacetime diagram where this path from the chair to the coffee shop is vertical. I'll label this spacetime diagram with time axis t and spatial axis x prime. From this perspective, my journey from the chair to the coffee shop is not a journey at all. It is me sitting still while the world is passing me by. In this coordinate, the chair is moving to the left over time, and the coffee shop is moving to the left over time. I was riding the chair to the left for a time, and then at t equals 1, I stopped, got off the chair, and waited for the coffee shop to arrive. And then when the coffee shop arrived, I hopped onto it, and I continued my ride to the left. Of course, if I am walking, jogging, driving, etc., from my chair to the coffee shop, I'm doing work this entire time to overcome the friction. The thing is, the chair and the coffee shop are connected by a large incompressible object called the Earth that was continually trying to push me to the left during the entirety of my journey. It actually took some work to resist the motion of the Earth and remain stationary throughout this time. Now, in practice, we wouldn't, of course, describe this scenario as working against the motion of the ground to remain stationary. Quite the contrary, I would say I am moving during this, and the ground is sitting still. However, if we took away the chair and the coffee shop and imagined instead two stars, such as the Sun and, say, Alpha Centauri, once we complete our acceleration here, there's no work to be done to maintain our inertia until we reach Alpha Centauri and have to decelerate. So in that situation, we would have no particular reason to adopt this coordinate system where the Sun and Alpha Centauri were stationary. We would look out each day, seeing the Sun receding behind us and Alpha Centauri approaching. It would be valid to claim that we were stationary and the stars were moving. Now, here's the idea of temporal phasing. It is to say that if I am sitting on a chair or at the coffee shop, it is appropriate to use a coordinate system where the chair and the coffee shop are stationary. But if I am traveling between the chair and the coffee shop at some constant velocity, it is appropriate to use a coordinate system where I am stationary. For more on this idea, you can go to www.spoonfedrelativity.com, click on Essays and Articles, select Galilean Transformation.php. You'll find some questions, diagrams, and animations that are related to this topic. In my next video, I'll be discussing temporal phasing using the Lorentz transformation and my Mathematica demonstration that shows temporal phasing in action. Oh, I should say, thanks for watching this video. I hope you will like the video and go out to the Spoonfed Relativity website, check out the pages. I'm also putting this demonstration out on ResearchGate.net. I'm also putting this demonstration out on ResearchGate, and I've got a working paper called Radar Time and the Temporal Phasing that I'm hoping to get peer-reviewed and published sometime soon. And now, thanks for watching.